There is no doubt we are in a new normal for the long haul. 2020 saw a good chunk of the world working from home. Is it going to change soon? I don't know. What I do know is that with your heightened online activity, more and more companies are preying on your data. They want to know everything about you, including your contact info, places you visited, spending habits, and the topic for today, what makes you happy or upset. They use all of this data in an effort to run an algorithm in the background to understand what variables make you grin ear to ear and what makes you want to tear out your hair. For either case, there is a sale to be made. Today we're going to build our very own sentiment model and include a little bit of psychology in our algorithm. So if you're interested, let's get started. Oh, and this is the kind of joy you can expect once you subscribe to this channel. So be sure to comment, like, and subscribe. So this is the way the sentiment is going to work. We're going to get this big paragraph of some sort, and right now obviously I'm using dummy data. Now understanding that Transformers processes this more of in a sentence structure, the next thing we got to do is we're going to go ahead and we're going to use Spacy. Now I find Spacy has one of the best ways to, or the best frameworks I would say, to actually take a paragraph and properly break it down into grammatical sentences. And then once you've done that, you're going to go ahead and you're going to get a list with different sentences that this paragraph has. And that's what we need to start feeding into our transformer model. All right, so now that we have this list of text or these lists of sentences, the next thing we're going to do is we are going to go ahead and use the transformer model, and we're going to use TensorFlow. But if you go to Hugging Face's website, you'll see the ability to actually use TensorFlow or PyTorch. I'm more comfortable with TensorFlow because I've been using it for a while, so that's what we're going to use. Then what you're going to do is you're going to take all these sentences out and you're going to give it a sentiment polarity, and by that I mean whether it's positive, negative, or neutral, along with a score. Now what I've actually done is I've gone ahead and created a filter on this. And the reason why I wanted a filter is I want to make sure that I can weed out anything that is a score of less than 0.9. And the reason why I want to do that is when I, for example, look at this second sentence here, it says negative 0.6. I actually don't want something that has only a 0.6 confidence level that it's negative. I actually want to make sure that when the algorithm does the math and does all this work behind it, that the score is actually at least 90%. Now you can change that threshold, you can make it 80%, 70%, you can even make it 50 if you want. But I went with 90%, but in the code, the way I'm going to design it is you have the ability to go and change that number on the fly. And what that's going to do is it's going to take out anything that has a score of less than 0.9. So any sentence that is left, I'm confident that when the algorithm, that when the transformer model actually gave it that polarity score, again, whether positive, negative, or neutral, that it actually has a strong confidence level against it. Now, before I go further into the transformer model, let's talk a little bit about RNNs, recurrent neural networks, and then LSTMs, which are a type of RNN. Now, historically speaking, RNNs and LSTMs were actually the models that were used, the preferred model that were used when we're doing sentiment analysis scores. Now there's a couple of drawbacks, but let's first talk about how that works. So let's look at this sentence, for example, and the sentence is, the fox is fast. The way this works is it's actually going to take every single one of those letters or those words, the fox is fast. It's going to feed it through the RNN and it's going to come up with some kind of a vector score. And that vector is basically going to tell us in vector space where that word sits. Now there are some issues with RNNs and LSTMs. First of all, they're very, very slow to train. And what I demonstrated to you there was that whenever an RNN is processing text, so if it's a sentence, it does it one word at a time. As a result, there's no parallel activity. What ends up happening is these sentences are encoded one by one, and at the same time, it's also hard to preserve context. And it's hard for RNNs to deal with really long sentences. And last, RNNs are sequential and they lack parallelization, and therefore are relatively slow. And what I mean by that is, because it's processing one word at a time, it takes a really long time for it to train it. Whereas when you move to something like transformers, if I look at this sentence, for example, the fox is fast and funny. So I just added and funny to the end. I won't go too much into the detail of how a transformer works. There's people on YouTube that could probably do a lot better explanation on this than me, but I will give you the high level of how this works. The way a transformer model works is it's got, very similar to an RNN, it's got an encoder and a decoder. So the encoder's on the left side, the decoder's on the right side. The decoder is really going to be beneficial in scenarios where you're doing like language translation, for example. So I'll sort of keep this to a sentiment context for now and not get into the language translation piece. But from a sentiment standpoint, it actually could take the entire sentence in, the fox is funny and fast. And what it does is that it'll actually go ahead and give it positional encoding. So it actually knows the word fox comes before fast and also comes before funny. Now, the reason why that's important, again, is context. And the good old classic example is I live to work or I work to live. They have the same words in there but mean completely different things. And that's why positional encoding is very, very important. But also on the line of context comes multi-head attention. And what multi-head attention does is it actually takes each one of those words and provides context for that word for that specific sentence. And it does one for every single word, so it knows how the is related to fox, is, fast, and funny. And it does that for every single word, and it'll do that multiple times, hence you have multi-head attention. So then it uses a feed-forward neural network to do some of the predictions. It uses softmax to really normalize the data and then come up with an output probability to say the probability that this is negative is X, or that this is positive or neutral is X. So that's as much as I'm going to go into the transformer model. And obviously we're using the BERT algorithm assigned with this. And again, it's going to come out of whether this is positive or negative. All right, so now that you have all this text, what are you going to do with it? Are you just going to take all of these, you have a positive and you have a negative, and what are you going to do? You're just going to take it and you're going to average it. Is that the right thing to do? So 1 for every positive, -1 for every negative, you add all of them up and divide it by the number you have? Probably not. There's actually a better way to do it. And so I was doing a lot of research around sentiment analysis. And one of the things that I came to understand is when people are doing document level or chat level or multiple sentence level sentiment analysis, it gets a little bit more complicated. So I'm going to give you an example of a document, for example. When I read an entire document, if I did this method, it assumes that every single sentence in that document holds the same weight. And that's not necessarily true. And that's because there's something called the peak end rule. And the peak end rule is a theory that the overall rating is determined by the peak intensity of the experience and at the end of the experience. It does not care much about the averages throughout the experience. So basically what this is saying is that when I'm reading an entire document, it's looking for what is that climax, what is that highest point that somebody's going to actually remember in that entire document. And then at the end of the day, when I've read through everything and I move towards the end of the document, that's going to be the most fresh in my mind. And the stuff that I read before that is not going to be that relevant, especially if it wasn't part of the peak intensity experience. So what now? So what do you do with this? So I have all this text, and the question is, what do you do with this? So this is something that I came up with. It's not necessarily something that has a whole ton of research behind it, but I will play around with this to see how this fares out. So the one thing we need to do is we need to highlight, what do you really want people to take away from this document? That's most important. And that's how we're going to identify the peak. The second thing is older sentences hold less weight than more current parts of the sentences. And that's the end. So the peak and the end. And then finally, what polarity, positive or negative, was predicted for each sentence anyways to begin with. So how would we address the peak, for example? Well, there's something called text summarization. And what text summarization does is it takes an entire document and pulls all the most important things out of that document. It basically summarizes it for you. And it'll summarize it using maybe 1 or 2 sentences from that document. And that is what the reader, in theory, would want you to remember from that document. That's the peak. That's the climax they want you to remember. So we're going to use text summarization to sort of mimic or use that as a proxy for identifying the peak. There may be better ways to do it, but this is just a POC. The second thing is we need to go ahead and define some kind of decay rate. And that is, as people are reading through things, they're going to forget the beginning of the document and give a lot more attention to the end of the document. And then finally, we're going to need some kind of a sentence matrix that helps us understand how each sentence was originally categorized and whether that's positive or negative in this case. We're not going to worry about neutral. So we have a sentence matrix. And this is very simple. So if you have, for example, in this case, I have 6 sentences. It's a 1 if it was categorized as positive, -1 if it's negative, and if you do have neutral or something, you can add that as a 0 or whatever you may want to do in that case. The next thing we're going to do is understand or try to find a decay factor. And what I've done here is I've just made it linear, and that is for every sentence as you go forward, you drop it by 0.01. In the code, you'll see that I've actually used an exponential decay, and we'll walk through that in a second as well. And then finally, text summarization, and that is give extra weight to the position in the nth sentence that is the peak. So if, for example, I have 6 sentences here, my first 2 sentences are not the peak, but my last sentence is the peak, then I want to make sure I give that some extra weight. Cool. So once that's done, we're going to take these 3 specific matrices and we're going to go ahead and multiply them together. And that's going to give us a weighted matrix that basically holds a score for each single sentence. And again, this is weighted. It's not the raw scores themselves. And because they're weighted, now I can take the mean of these numbers and then come up with a final score. And the way I've just categorized these, I said if you're between 0.5 and 1, you're positive, negative 0.5 to 0.5, you're neutral. And otherwise, between negative 0.5 and negative 1, you're considered negative. You can come up with whatever classification you want. But now, the beauty of this is this actually has some weighting, and it has some context, and it has some actual psychology built in on how people actually read and how people actually remember. So now let's get into some more examples. All right, so I've already gone ahead and created the code for all of this. What I'm going to do is I'm going to walk you through the code, and we're going to run it for each specific area that we cover into the presentation. And I've started this off really as capping it with a class of sentiment, and under that I've got a constructor. I've got something that's going to go ahead and break the sentence up into lists, and then that's going to go ahead and find the raw polarity for each of those lists. Now once I get all these sentences, it's going to tell me, based on these sentences, what should my decay rate be. So this is my linear function. I basically set it to 0.01. I've also created one that has an exponential, so I can basically use either one of these two functions. And both of them give me a pretty decent reading. Finally, I can go ahead and find the peak. And the peak in this case is going to be my text summarization, for which I'm going to use a transformer model. It's a pre-trained model, so I don't need to go ahead and further train it. And I've just used that pre-trained model to go ahead and find the peak sentence. If you were to put something like this into production, I would probably say take some raw data and go back and train the model with some of your own data for some of your own use cases. A lot of the hard legwork has already been done, but you can go ahead and train your model for that as well. Finally, we're going to go ahead and get that peak position. And it's going to go ahead and create that matrix for me. And that matrix is going to tell me whether it's a 1 or whether it's a 0.9 based on the presentation we just saw. And then it's going to go ahead and compute the final score. So we're going to do a lot of this. I've just got this prepared text that I just got from online, a couple of articles. This one was around Walmart not being able to supply the PS5s because there were some bots that basically bought up all the inventory. I actually created a different video that shows you how you can create your own friendly bot that's not going to go buy the inventory, but help you identify who's got the inventory. I'll link that up above, and you can take a look at that as well. So let's go ahead and run through this example of how this works. So let's go ahead and run break sentence first. So I'm going to go ahead and run this first, Python, and I can just use Starler because it's the only document there that does that. And of course, I forgot to go ahead and go into my virtual environment. So source venv bin activate, and now I can run that command again, and it's going to run through all this, and it's basically going to take this raw sentence that I have here, raw text I guess, and it's going to go ahead and create a list for this. And so all this entire sentence now has been broken up into lists using Spacey. And Spacey does a really good job of identifying context and what belongs to a sentence and what doesn't. It can identify punctuation very well, so that's why I recommend you use Spacey. All right, so now we're going to go ahead and run the raw polarity. My confidence level is 0.9. I'm using the sentiment analysis pipeline from the transformer model. What I've done here is I've said, because I've gone ahead and added a filter, I said, how many sentences do I have to start with? And then how many sentences do I end with after I've completed my filter? And then it's going to go ahead and return the actual sentences and then the matrix result for me. So let's go ahead and run this and see what it looks like. So let's clear this out and go ahead and rerun this. All right, so it's gone ahead and taken every single sentence. It's basically said before I had 15 sentences in this document. After I've applied my filter, I'm down to 13 sentences. And that's my confidence. I want to make sure that it's got at least 90% confidence with its rating. And so these are the individual sentences, and anything that is a negative one was ranked as negative. Anything that was a positive one, which in this case was one sentence, was ranked as a positive, or two sentences I should say, was ranked as a positive. All right, so for the purpose of the actual text weights, you can again use this linear function. I'm going to go ahead and use this exponential function that I created. We're going to scroll down here and run that, and you're going to see the output of that as well. So what it's basically said is the most current sentence, or the sentence towards the end, will get a weight of 1. And as we read this entire document, we're going to go down and exponentially add a decay factor. And because there's 13 different sentences that we're looking at, it's going to do this 13 times. And so this is just exponential decay. So that means that you'll probably remember about 79% of what you read towards the end of the document for sentence number 1. And then you'll remember obviously everything that you just read for the last sentence because you just read it. So that gives you your decay factor. And that's one of the different matrices, remember, that we're going to multiply against. So now with find peak and then get peak position, where we're sort of run both of these simultaneously. And what these are going to do is first it's going to go ahead and identify the actual peak of the document or the summary text of this document, and then it's going to go and find its position in the actual matrix to see whether it's sentence 1, sentence 5, or whatever it may be. So let's go ahead and run both of these here. So I'm also going to go ahead and add a line here that says print s dot get peak position. So let's run both of these together and we'll see what it does. Let's clear this out, run this together. So let's go ahead and see what those sentences actually were. And it's buried right there. Retailers are trying new tactics as the pandemic has broadened bot-powered reselling to new product categories. So there are, in this case, 3 sentences. 1, 2, 3 sentences. Though for whatever reason, we've only identified 2 sentences in this actual matrix. And there's a reason for that. And the reason could be that one of these sentences was weeded out through our process, because when it's actually doing this, find the peak, it's looking at the entire text and not the filtered text. Because even if I filtered it out, I want the algorithm still to go back and say, hey, maybe something was filtered out, but it is important. And we can address for that later, but I just wanted you to understand that. Or the other thing is the text actually wasn't split up properly. This is actually, in fact, one sentence. When you go ahead and read the document, you'll notice that this is all part of the same sentence. So that is an issue with Spacey that we need to go back and do some testing with as well. But regardless, I've seen both of those scenarios. Now, there's another important thing that you need to understand when you use a transformer model, and that is this sentence right here. Each sentence is actually capped at 512 characters. I've got apparently a sentence that is 847 characters, and as a result, it truncates that. So whatever is the difference between that, it just ignores it as a part of the algorithm. There's ways to work around that as well. You'd have to build sort of a custom module or a custom function to deal with that, but it can certainly be dealt with as well. But from an educational and context perspective, the theory and the methodology still make sense. All right, let's go ahead and do the final assessment now. And that is, we want to go ahead and understand what the final score is for this document. So we're going to hit get final score. I'm going to get rid of all of this stuff here. And we'll say get final score. Perfect. And we're going to go ahead and run this. And there you go. So basically this sentence, or this document I should say, has been categorized as negative with a final score of negative 0.508. And again, if you go back to my presentation, I basically said that would be categorized as negative. Now let's go ahead, for the sake of it, try some other documents. So this document I told you was about Walmart not having the PS5s and a lot of people being upset about it. This one is about just dogs having animals with stress relief. So I mean, obviously I think when you just think about that conceptually, that should ring out as a positive document. But let's see. I'm just going to run the actual positive score on it. I'm not going to go through everything. And we'll see what this document comes up with. Now I can even create a loop if I wanted to run all of these raw documents, but we won't do that just because it's going to go ahead and compute everything like crazy, and it's going to take a long time for us to get the final result. So this document had 41 sentences. We filtered it down to 37. This uses a BERT model, and I believe it's distilled BERT right there. And that is basically just one of the models you can use. BERT is a very popular model. It basically uses bidirectional reading, so you read both ways to get context and not just one way. And then distilled BERT is a subset of BERT, which is basically used for stuff like this because it's a lot more efficient and it still holds about 97% of the accuracy rate of original BERT. So that's basically some background on BERT. Now this document was classified as neutral with this score over here. And then let's just run one last one around heat stroke protection, clean air. Cool. And this last one was classified as neutral as well. So we have 3 neutral articles, which is fine. I was hoping one of them was going to give us a negative result, but that's okay. You know that basically it gives us a score, and the score is going to determine whether it's negative or not. So let's talk about some of the challenges with sentiment analysis in general. First of all, when you look at something like the peak end rule, the peak is highly subjective to the reader. Based on the interest, the climax for the story could be different. So for example, if I'm reading an article on car parts, there are people that get excited with the engine versus somebody who gets excited through the types of tires you have, whether they're performance tires or not. And so the peak for that individual can be a lot different. But what the algorithm is trying to do is work on the law of averages. And that is when you take a mass amount of data, you get a very good understanding of what people like and what people don't like. And you can categorize things, and you can say there's a certain population, or weight it to say that maybe we don't weight everything equally, and maybe the engine gets a higher weighting than car parts for this subset of the population, or vice versa. So you can overcome it, but it's still something that is a challenge. And so using an out-of-the-box solution is sometimes not the greatest thing to do, unless you really know what you're doing. The second thing is, as I pointed out earlier, one of my sentences was 847 words. And as a result of that, it's truncated a good portion of the actual text. And that text that got truncated could actually be the meaningful part of the data. So again, taking it out of the box, not the best thing. You have to work around it to make sure that you can make it work for your model. Now, a model should be trained for one's own organization or purpose. So if I'm going to go ahead and train a model for something that's a chat support from my telecom provider versus me going in person and speaking with somebody like Apple for Apple support, because you can actually go ahead and understand the sentiment of that conversation as well if it's recorded, if it's in person. The model is going to be slightly different because your interaction is slightly different as well. So you need to train it for your data. And then finally, I would say sentiment analysis is definitely moving in the right direction. It still requires a lot more customization and dollars spent. And what I mean by dollars spent is a lot more specialist type people to come and go pre-train the models and write the right algorithms. Using something like the transformer model is a great way to go ahead and process the data, but what you're going to process, how you set up the data, still needs to be done in the background. So this was a educational, we'll call it a POC for lack of better words. Hopefully you guys learned a little bit more about sentiment analysis. And if you did, consider liking and subscribing, and we'll talk again soon. Bye-bye.